Hello everyone, welcome back to Math with Allison. Today we're continuing our series on derivatives. If you haven't already, make sure to check out some of my previous videos. They're linked here in the corner. Click that little eye and it'll get you there. Otherwise, specifically, we're talking about implicit differentiation and how we can apply it. So let's go ahead and dive into it. Question, what the heck is implicit differentiation? And it's when we're given a function that's not perfectly y equals something, something, something in terms of x. So we can still find the derivative even if it gets a little messy. So here we have an example. It's just the equation for a circle. So we have x squared plus y squared equals 1. And our goal is to find dy dx or y prime. Both of them represent the first derivative of y. They're just used in different representations. So you can use whichever one you prefer. In this case, I'm going to use y prime. So let's go ahead and dive into this. Our goal is to take the derivative of both sides. So I'm going to take d dx of both sides. So I get x squared plus y squared equals the derivative of 1. Notice here that we are taking the derivative in terms of x. So we have d dx and d dx. But we have a y involved. That's going to be our issue. We cannot take the derivative of y perfectly when we're taking it in terms of x because they're two different variables. So it has a funky little look. First, I'm going to take the derivative of x squared. No issue there, they're the same variable. So here I'm going to use power rule and I get 2x. Now what I'm secretly going to do on the y squared is I'm going to use chain rule. So I'm going to go ahead and label my outside and my inside. So here I get the u is equal to y and my g of u is equal to u squared. If you haven't seen chain rule yet, make sure to check out my previous video. Super helpful. And now I'm going to find both derivatives of these. So I'm going to mark it as u prime and g prime of u. Here, g prime of u, I can just use power rule, so I get 2u. But now we have an issue with u prime. Again, we're taking the derivative in terms of a different variable. And so actually what I'm going to do is I'm just going to label it as y prime. Or if you like it in terms of this fancy one, you can also use that. So what this actually becomes is y prime times 2u, and I'm going to replace my u back with y, and that's my derivative using implicit differentiation. It's a secret chain rule going on here. And then we get the derivative of 1 is just going to be 0. So now what we want to do is we want to isolate my y prime. I want to get it all by itself. So I'm going to subtract 2x from both sides. I get y prime times 2y is equal to negative 2x. Now I can go ahead and divide both sides by 2y in order to get y prime all by itself. So here I get negative 2x divided by 2y, and I can simplify that one more time by dividing out the 2's, and I get negative x over prime. Negative x over y. So here we see we had a function that was not perfectly in terms of y. We didn't have y equals blah, 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 but we can still find the derivative. Let's go ahead and see the application of this. We want to find the line tangent to x squared plus y squared equals 1 at the point 1/2 comma root 3 over 2. So in order to find the line tangent, we need the line formula. Here it's y minus y1 equals m times x minus x1. We already have x1 and y1 because of the point, and actually we already found the formula for the slope. M is equal to the first derivative at the point. So if we remember here, our derivative is equal to negative x over y. So here I get negative 1/2 divided by root 3 over 2. Let's go ahead and simplify that out a little bit. I'm going to rewrite it as negative 1/2 divided by the square root of 3 over 2. And when we divide, we can actually multiply by the reciprocal. So we can multiply by 2 over the square root of 3. Here we get that the 2's divide out very nicely, and we are left with negative 1 over the square root of 3. I'm going to go ahead and plug all of this into our equation. So here we get y minus square root of 3 over 2 equals negative 1 over the square root of 3 times x minus 1/2. Here y minus the square root of 3 over 2 equals negative x over the square root of 3 minus, and that becomes a plus, 1 over 2 root 3. So y, and I'm going to go ahead and add over that root 3 over 2 is equal to negative x over root 3 plus 1 over 2 root 3 plus root 3 over 2. In order to make a common denominator, I'm going to first get rid of the radical. So multiply this one by root 3 over 3. And when I rewrite this, I get a 6 in the denominator. So root 3 times root 3 is equal to 3. So 3 times 2 is 6. So now I want to make this denominator the same. So I'll multiply this by a 3 over 3. And now I can add a 3 root 3 over 6. And now I can go ahead and combine these. So here I get negative x over the square root of 3 plus 4 root 3 over 6. And here is my equation of the tangent line. So that's the application. We can also still find tangent lines without a super nice function. Let's go ahead and see another example of this. So we're going to find the equation of the line tangent to the curve x squared plus xy minus y cubed equals 7 at this point 3, 2. So first, let's go ahead and use implicit differentiation. So I want to take the derivative of both sides in terms of x. Alrighty, so let's go ahead and look at our first term. Here we have the derivative of x squared. That one's super nice. We know the derivative is 2x. And now we need to take the derivative of xy. So I'm going to have two different functions here, and I'm going to use product rule. So let me go ahead and set that up. Alrighty, so the derivative of x is just going to be 1, and the derivative of y, remember, it's just going to be y prime. It's not super nice. They're different variables, x and y, so we can't take the derivative of y in terms of x. And now I can go ahead and fill this in with product rule. So I'm going to multiply these two together. So I add y, and now I'm going to multiply these two together, and I add x times y prime. And now we have one more derivative to take, and it is y cubed. So with this one, I'm going to do the chain rule. So I have the derivative of the outside at the inside, and we're going to multiply it by the derivative of y. In our case, that's going to be y prime. And now I have the derivative of constant, which just goes to 0. So now that we have this nicely multiplied out, I want to go ahead and isolate all my y primes. So I keep all the terms with y prime on one side, and I move all the other terms to the other side. So I'm going to subtract the 2x and the y. So now that I have these isolated, I can go ahead and pull out the y prime since they both have one in common. And now I'm going to multiply it by the leftovers. So I have x minus 3y squared. And now I can go ahead and divide that over. So I get y prime is totally isolated, and I have y prime. So remember, we're trying to find the line tangent at the point 3, 2. So what I want to do is I want to find my slope. My slope is equal to y prime at that point. X is equal to 3, y is equal to 2. And I can just plug that in. So I get 2 times 3 minus 2, all divided by 3 minus 3 times 2 squared. When I multiply this out, I get negative 6 minus 2, all over 3 minus 12. This is negative 8 over negative 9, which simplifies to 8 over 9. So now I can plug this into the formula. Y minus y1, which is 2, is equal to 8 over 9, x minus x1, which is 3. So here y minus 2 equals 8 over 9x minus, and that 3, when I multiply it by 8 over 9, the 3's divide out, and I'm left with 8 over 3. So here I can add 2 to both sides. And remember, 2 can be rewritten as 6 over 3. So when I do that, I get y is equal to 8 over 9x, and now I'm going to subtract 2/3. And here I have the line tangent. Let's go ahead and see a different type of application. We can find second order implicit differentiation. So that's either viewed as d squared y over dx squared or y double prime, depending on which notation you use. And here we have our function x plus y is equal to sine of y. So let's go ahead and do this thing. We are going to go ahead and take the derivative of both sides. So here I'm taking d dx of x plus y, which is equal to the derivative d dx of sine of y. When we take these derivatives, first I have the derivative of x is just 1, and the derivative of y is going to be y prime, not going to be 1. and this is going to be equal to the chain rule. So here we have the outside is going to be sine of y, and our inside is just going to be y. So first, I'm going to take the derivative of the outside. Derivative of sine is cosine, and the inside totally stays the same. And now I need to multiply by the derivative of the inside, which is y prime. So now what I want to do is isolate my y primes, which means I want to get them all to the same side. I'm going to subtract over that y prime. So I have y prime times cosine of y minus y prime. Now that they both have a y prime in common, I can go ahead and pull it out, and I have my leftovers cosine of y minus 1. Now I can divide that over, so I get 1 over cosine of y minus 1 is equal to y prime. So now we found our first order derivative. Now we can actually use this to find the second order derivative. So again, I'm going to take the derivative of both sides. So I get d dx of y prime is equal to the derivative of 1 over cosine of y minus 1. So here, the derivative of y prime is just going to be y double prime. So that doesn't change at all. And now what we're going to do here is quotient rule. So I have my numerator is 1 and my denominator is cosine of y minus 1. I'm going to go ahead and write that out. Alrighty, let's go ahead and do this thing. So the derivative of 1 is just going to be 0. And now we need to find our other derivative. Again, we're going to use secret chain rule here. So we're going to do the derivative of the outside. Derivative of cosine is negative sine of y times the derivative of the inside, and then the derivative of negative 1 is just 0. So here we can substitute back in what y prime was originally equal to. So here I have negative sine of y times 1 over cosine of y minus 1, which actually I can go ahead and rewrite that as negative sine of y all over cosine of y minus 1. So let's go ahead and plug all of this in. So I gotta start at the bottom and work my way to the top. So I get 0 times cosine of y minus 1. That's just gonna be 0. So I have 0 minus, and now I start at the top, work my way to the bottom. And notice these two negatives become a giant plus. And then all of this is over the denominator squared. Let's go ahead and rewrite that down here because we got a lot going on. So I have sine of y over cosine of y minus 1. And now I'm going to multiply that by 1 over cosine of y minus 1 squared. So here I can combine the denominators. So I get sine of y and the numerator stays the same. But now I have 3 cosines of y minus 1. And here that's how we get our second order differential equation. So you have to use the first order in order to get the second order. Let's go ahead and do one more example. So we're going to find y prime or dy dx of that entire function. And notice here we actually have to use product rule twice. We have x times y, and we also have x to the power of 3 halves times y to the power of negative 1 half. I'm going to go ahead and write all those out. Okay, let's go ahead and find all these derivatives. So first we have f prime of x is equal to 1, and g prime of x is equal to y prime. And now we're going to look at our other f of x. So here I'm going to bring down the exponent and subtract 1, so I get to the power of 1 half. And then similarly for g of x, or g prime of x, we get negative 1 half y. And now I'm going to subtract 1, so I get negative 3 halves. But be careful because we're working with y, so we have to multiply by the derivative of the inside, which is going to be y prime. So now I'm going to go ahead and use all of these product rules together. And now we got to take the derivative of our constant 2, which is just going to be 0. So what we want to do is isolate all the terms with y prime. So here I have a y prime in this whole term, and I have a y prime right here. So I'm going to subtract over all the other terms that don't have a y prime. Alrighty, so now that I isolated where all the y primes are, I can pull that y prime out. Now I can divide both sides in order to get y prime all by itself. And there we go, we got our derivative, but remember, we're trying to find the line tangent at the curve at 1, 1. So in order to get our slope, we have to plug in that value of 1, 1. So y prime at the point 1, 1. Let me go ahead and do that. 1 raised to any power is just 1, so that's kind of nice. I can just substitute that in there. So here I get negative 5 halves in the numerator divided by 1 half in the denominator. I can rewrite that as negative 5 over 2 divided by 1 half, which means really I get to multiply by the reciprocal. And here I can see that the 2's divide out, and so what I'm left with is negative 5 as my slope. So let us go ahead and plug all this into the equation. So y minus y1 is equal to m times x minus x1. Let's go ahead and solve this out just a little bit. Y minus 1 equals negative 5x plus 5. I'm going to add 1 to both sides. So here I get y is equal to negative 5x plus 6. And that is my line tangent. So that's all I have for us today on implicit differentiation. If you enjoyed this video, please leave a thumbs up and comment other topics or videos or problems you'd like to see done. Thanks for watching.